Welcome, ladies and gentlemen. Today, our little off-grid enclave community is gonna have a look at an unusual method of generating heat. The concept I'm talking about is using a compost as heat source. Of course, what comes to mind first when people hear compost is the classic household compost with a mixture of garden materials and kitchen waste. For this concept, however, a compost with much more wood as basic ingredients is used. As this technology is a rather unusual approach, the research into the optimal composition of the compost is still at early stages. Usually, mixtures consist of at least 70% shredded wood waste and up to 30% of different organic compounds such as cow dung, grass, or kitchen waste. Here is a picture of a finished compost heating project. As you can see, a compost for heating purposes looks very unspectacular. It is generally much bigger than your casual household compost. The basic idea is nothing fancy or complex. During the process of turning wood and biomatter into humus, bacteria produce heat. That heat is harvested using water as medium and pumped into the house. There it can be used for various appliances like heating or warm water. What is the main benefits of using such a heating? First off, it's a renewable energy source that can be locally sourced. It is rather cheap as it uses low quality wood waste as main resource and does not require complex technical parts. It is quite safe as the compost naturally will not rise above 65 degrees Celsius in temperature. It has a very long duration. Depending on the composition of the compost, 18 to 24 months of heat production are possible. Its waste product is a resource. After the compost is finished and does not produce heat anymore, it turned into humus, a valuable garden resource. How then do we get this done, and how does the heat transfer exactly work? For starters, the shredded wood waste and biomatter is mixed properly and watered well. The material is compressed by stomping. About each 80 centimeters, special plastic tubing is run in spirals through the construct. This is the part where the heat transfer to the water happens. Keep adding more and more material until you reach the desired dimensions. To give an idea about those dimensions, I will put up a spreadsheet of numbers here. Once again, I would like to point out this technology is in its very early stages of research and the numbers should be treated as estimates at best. Using a different construction form, different piping, different spiral diameters, compost compositions, and many other parameters can easily change these numbers by about 50%. Before we head further into technical details, this is a good time to poke for a like if you enjoyed this content. Subscribe and hit the bell if you want to keep up to date. Thanks a lot. If you have questions, ideas or input, don't be shy, hop on our Discord. The link is down in the description. Okay, now we have the concept of the heat source sorted, and all we have to do is integrate it into our existing heating cycle. For our project, we will be using a tube heat exchanger and set it up for counter current flow. It will be showing you guys some numbers for these type of heat exchangers to give an idea of the dimensions. This type of heat exchanger was chosen for its flow capacity ability compared to plated heat exchangers. Plated heat exchangers have a tendency to clog and have difficulties with calcareous water. For our project, we want to harvest about 10 to 12 kilowatts of heat energy, which means we will need about 100 cubic meters of compost or about 35 tons. We will not be using a round base but a square base setup with isolated walls. The expectation is that during the winter months the isolation will increase the efficiency. After some glorious napkin math and consultation with experts on the subject, a 88 kilowatt heat exchanger was chosen. A quick rundown on the math. The heat exchanger is rated at 88 kilowatts with about 60 degrees Celsius temperature difference. Our expected temperature difference, however, is more between 20 and 30 degrees. At 20 degrees, we will have about 40% left. That rates our heat exchanger at about 35 kilowatts. We will be using a mixture of water and frost protection as a medium. That reduces another 10%, dropping the heat exchanger to about 31.5 kilowatts. Throw in some isolation loss of 5% and we have around 30 kilowatt effective real heat transfer. Compost heating should not be perma-run, but run in cycles to give the medium time to warm up again. Compensating for these cycle times, 30 watt kilowatt heat exchanger for 10 kilowatt heating should be a reasonable rate. Of course, there is still many variables such as cycle time, flow speed and such to be fine-tuned once the setup is ready. I will keep you guys up to date on the progress. Thank you for watching, enjoy your day and make it count.